My name is Bernhard Stribny. I'm coming from the Federal Institute for Geosciences and Natural Resources in Hanover, Germany. We are carrying out international research on fuels, on energy raw materials, on mineral raw materials, and on all questions of geosciences. Today, especially, I will focus on the exploration of minerals, means how to find minerals and how to use it, and we will a little bit reflect the problems of conflict minerals on this globe. Thank you very much for your attention. It's a pleasure for me to be here today and to tell you something about geosciences and how to find minerals and what we are doing with the minerals on this planet. So as you all may know, there would have been no Stone Age without rocks. So easy question. Did you use today, before coming to here, a mineral? Yes or not? Yes. Which kind? Salt. Salt? Okay. What else? Toothpaste, yes. There's calcite in the toothpaste. It's an abrasive material. And even sitting here, you're sitting in a building made out of concrete and steel. So we are really depending on a lot of minerals, and you have a lot of them even within your body. Well, so it's just some figures, some facts on minerals. As you can see here, in the lifetime of an average German people, you are consuming about 1,000 tons. That means 40 kilos of mineralic raw materials per head and per day. And as you can see here, with this figure we are lying 10 times higher than people living in developing countries. And I highly appreciate that some of these even are here in this room. That means 20% of the world population consumes 80% of the natural resources. That's Japan, Europe, and North America. But this is changing. Now India and China is coming to being global players. And of course, there is a huge demand in raw materials. And it's a really competition how to deal with this fact. Well, so the first take-home message for today is, if it can't be grown, it has to be mined. That means everything you see around here, you use every day, it's coming from forestry, from agriculture, or it comes out of the mine. So everything we do in our so-called modern world, it relies on natural resources. So, and as you can see here, in the past, there were small-scale mines with high grades but low tonnage. The miners, they are digging out with a hammer very vein deposits. And as an example, in the Harz Mountains in Germany, 400 years of silver production, the same tonnage of about 400 tons of silver, we do now in the Polish Kupferschiefer within 3 months. Today, we are mining huge deposits in open pits or underground, so-called high tonnage, low grade, because we are able to treat these low-grade ores and to enrich them by beneficiation up to the smelter and up to the final metal, for example. So, of course, we are making our complex world a little bit easier. So, mineral deposits, the second take-home message is result from ore or mineral forming processes. That means everything is moving on this planet. And there are a lot of geological environments where specific minerals are enriched. So, for example, in the sedimentary environments, we found sand, gravel, boulders, clay, whatever minerals, it's easy to find to form bricks and concrete or whatever. And there are some processes, they are deep in the subsurface with temperatures higher than 200 degrees with high pressures. And of course, we have all the magmatic events. You can imagine if there are melts with several cubic kilometers are intruding a cold crust, having a heat from 1,200 degrees Celsius. We have the formation of granites, of basalts, all the suites of volcanic rocks. We have volcanic ashes, which are used for forming bricks and for agriculture and so on. So, mineral exploration, the question is, we are mining out, we are producing out of anomalies. That means we do not use a normal kind of rock, of sand, but we use specialized rocks with special volumes, with special qualities. For example, an ore deposit must be enriched in iron, in copper, in manganese, whatever. So to look for these geochemical and geophysical anomalies in the crust on this huge planet, we need to have special strategies how to find a mineral deposit, how to find an iron ore deposit. You can't go out of Wien and take a truck and make a drill hole, so that's not that easy. So what you have to do is, you first of all, you take some maps, you look where are, for example, former mining activities in medieval times even. You make some models to think which kind of structure might be convenient, which process might be, let me say, result in a salt dome, a salt diapir. And are there, for example, some minerals in the vicinity of this structure which might be interesting for mining? And you make some metallogenic models. You think, where are the metals coming from? How do they precipitate as sulfides in a, let me see, marine sea basin or whatever? And you had to combine this geological data, expert data, you make a validation, and then you can develop an exploration concept. So all this is done in the office just by thinking, combining, making a strategy. But beside of the geological facts, we of course had to take care about geographic, the political situation, markets, infrastructure. So there might be totally comparable deposits, let me say in the middle of the Sahara and at the east coast of Canada. Of course, everybody would invest in the east coast of Canada. It's much easier, it's politically stable. So even the deposits are comparable with the same grade and tonnages. That's a benefit. It's an advantage to go, let me say, in this type of rock, then making, let me say, a first infrastructure, building up railroad lines for 2,000 kilometers in order to get your ore shipped on the harbor. Well, and having this strategy, having some target areas, well, how do we start to find a deposit which might be small in size and high grade? So today we're starting with so-called remote sensing, even from the satellite scale. You know, this meeting goes on scales, time scales, and scales in the nature. So first of all, it's very easy, and for example, you can cover a huge area within several minutes by flying over with the satellite. And we have a lot of specialized tools, spectroscopic characterization of mineral deposit. That means we have a special, let me say, physical features we can measure from the surface of a landscape here in Africa, and we can even map some minerals which are present on the surface with a distance from, let me say, 20 kilometers apart. So these are high tech developments of the last centuries, last decades, where we are able to map this globe from satellites. So that is the first step in order to get some target areas investigated. The next step, of course, is airborne. It's an aeroplane or a helicopter. The advantage of a helicopter is he can fly more or less parallel to the morphology. That means the distance between the helicopter and the surface is more or less constant. And then again, we can measure a huge variety like gravity, like electromagnetics, whatever. That means geophysical properties which are unnormal to a normal continental crust. And we find some anomalies like here you can see it's an island in the North Sea, and we can, for example, map sweet water lenses in salty seawater by the helicopter geophysics. The third step, after satellites, after the helicopter, okay, then the people, the geologists had to go out into the field. Here, of course, I cannot scan several hundred square kilometers. So it's more or less a downscaling in scales. That means here we have some electromagnetic tools, and maybe we can map per day 100 by 100 meters, but we get, of course, more detailed information than from the satellite. So we have different steps to find out, for example, a clay deposit in the subsurface in an open desert like here in China. Well, of course, besides of geophysical properties, there are a lot of geochemical properties which are also indicating some normal mineral enrichment in the crust. And the same holds true for the scales. So we start, for example, with sampling stream sediments. So within a stream river, you have sediments which cover from a whole area which is dewatered by the stream systems, and then you can take the sediments and you can look for arsenic or for cadmium or whatever minerals typical for some deposits, but also relevant for environmental question, like we have heard yesterday, the so-called baseline studies. This is also done by geophysical or geochemical projects carried out in order to get the baseline before starting an open pit mine, for example. And there are a lot of, let me say, fluorescent tools where you can make some drill course, for example, and look for detailed with a lot of high-tech equipments. And then, maybe after 1 or 2 or even 3 years or longer, at the end, then you define a drilling target. Because drilling is very cost-intensive. Drilling in hard rock, 1 meter might cost 1,000 euros. Drilling for 3 kilometers means 3-4 millions. And as a geologist, you can do it once or twice, drilling just into nothing. Otherwise, you will look for a new job. You know? So it's really a challenge to define a drilling target. To say, okay, I invest 2 millions, let's drill for 2 kilometers into the depth. I hope to find something. So we have special drill rigs. You make drill cores, and then, of course, you cut them with a saw, and then you sample these drill cores. You make some special high-polished sections which you can investigate under the microscope. Here you see some copper and sulfur minerals, but this tiny one here, that's pure gold. And that's nice to see under the microscope. And even more in detail, you look the scale, another scale question. So these tiny mineral here, it's a Marenskyite. You will never see it in your life. It's a palladium telluride. So tiny, tiny crystals, a million of a meter small, but high value, as we have heard yesterday. Your 1 ton is 25 million euros per ton. Well, but not only on land, we are now starting to investigate for mineral deposits in the open sea, offshore. Here, that's the new research vessel called Sonne. The old one just ended up with their activities, and the new one, what we are doing here, we are going out looking again on the total globe. Again, we are defining exploration targets. We are sitting in our offices and let's say, where on the big oceans, where might be some mineral deposits on the seafloor, and even in 3, 4, 5, 6,000 meters water depth. How do we can detect them, and how can we explore them? So we are looking on the globe, and I can see here, you see some red dots that are the so-called mid-Atlantic Ocean ridges. Here, oceanic crust is formed due to the drift of Africa to the east and America to the west. So the Atlantic Ocean opens, and in the center of this opening, here's Iceland sitting as an island formed by oceanic crust, the only one where the volcanoes, the submarine volcanoes, formed an island directly on these huge ridges. And of course, due to these volcanic activities at the seafloor, there are hot waters. We just measured 400 degrees at the bottom of the seafloor. So it's really hot, and it might be a commodity for let me say, a spa and whatever, wellness swimming or wellness diving down to 400 degrees Celsius. Okay, so we defined again some research areas and looking, for example, for polymetallic sulfides at the seafloor of the Indian Ocean. And these research areas, for example, you had to apply at the seafloor authority of the United Nations. That means every country can make some claims, stake their claims, but you have to apply for the claims, and we did it some years ago in the Indian Ocean and in the Pacific as well. So these are the processes I told you which are forming minerals on the seafloor. We take so-called remote ocean floor vehicles, about 4 million euros, such an equipment, which equipped with cameras, with sampling tech tools. So we're going down 4,000 meters to the seafloor, and here you can see these hot water with steam, with ashes, white or black, we call them black smokers, coming directly out of the seafloor due to these magmatic processes. And the result, if you sample such a structure, if you cut it in the lab, you can see here the walls, and here's the chimney in the middle, and it's nice goldy glittering minerals. It's an chalcopyrite, a copper-bearing minerals, and this is a process behind some, let me say, 2-3 kilometers. We have a magmatic heat source in the subsurface. The cold seawater is more or less cycled in an art hula hoop cycle. And in the center, we have the smokers with the hydrothermal vents. And here, minerals are precipitated like chalcopyrite, pyrite, sphalerite, and galena. That's a lead sulfide, that's a zinc sulfide. And we have the zonation on the seafloor, and we can map the smokers. We can make some geophysical and geochemical investigation. And we can decide whether the tonnage and the grade are sufficient for a future open sea or blue mining, or however you want to call it. It's a future resource. It's not a reserve up to date. Today we are just carrying out research. And again, we are combined with some biologists and ecologists making baseline studies in order to see what kind of environment and ecosystem is present in these smoker environments. Another very interesting commodity on the seafloor are the so-called manganese crusts and manganese nodules. You can see here they are, let me say, so 10-20 centimeters in size, round bowls made out of some manganese oxide, but they are carrying other minerals, other metals like cobalt, copper, and nickel, so they are quite interesting. And the main reason why we are carrying out metallogenic research in the open sea is that, let me say, onshore, Germany is very small, highly populated, and the open sea, that is, as I told you, managed by the UN, but it's an open area, and let me say in 100, 200 years, I think we will be able to take out most of our minerals maybe from the open sea. And you see here they have a lot of very small growth rates, some millimeters per million years. The same holds true for these cobalt-bearing crusts, which are found on submarine sea mounts. And again here, very, very low growing rates because the metals are coming out of the seawater and precipitate by geochemical processes in the sediment or on the sea mounts. Here we have such a nodule, and you can see you have concentric rims, growth rims, and then it gets more and more diverse, but it's still a very stable structure, and of course you might easily can mine it out even from 4,000 meters water depth. Well, so these are the first part of my presentation, talking about how to find minerals. But now we are looking a little bit, what we are doing with minerals. And we have, in many places of the world, not in all of them, the so-called resource course or the paradox of plenty. what's meant? Some regions with abundant mineral resources tend to have less economic growth, worse development outcomes, higher environmental impacts than those with fewer natural resources. That is a paradoxon. What's the reason behind? The reason behind is that in these countries, the economy is focused only on one sector, mineral extraction. Of course, we are trading all minerals, especially metals, on a globalized international market like the London Stock Exchange. That means if there are market swings, if there are volatile prices, and if there are strong shifts with demands and supply, you cannot calculate what gold price will be in 2 years. Nobody can tell. So if you are focused on one sector and the gold price is going down, the whole economy is going down. And of course, we have ineffective, unstable, and corrupt institution administrations. Here, I will tell you, we are from our German Federal Ministry for International Cooperation. We are cooperating in many, many developing countries in the world, especially in capacity building due to, let me say, mining authorities and administrations in order to make, let me say, this paradoxon of plenty less effective. Well, that's some examples from so-called environmental impacts. It's Pechenga and nickel sulfide deposits far up in the north in Russia and the Kola Peninsula, close to the Norwegian border. So we had an excursion there, and as you can see, it looks like the moon. There's nothing more. No plants. The rocks are even having some brownish crusts. Why? The reason is they smelt nickel sulfide. And when smelting a sulfide, sulfide dioxide is emitted to the atmosphere, and it's the reason for the so-called acid rain. You have heard it 20 years ago. We discussed it even in Germany, acid rain, but we were able to solve the problem. How? We have so-called, we can, let me say, transfer sulfur dioxide together with calcite. It's forming gypsum. So we have so-called gypsum from these plants, and we can sell it like natural gypsum as well. But by this process, when transferring SO2 to gypsum, CO2 is emitted. So what we are now looking for in regard to climate change is a process how we can transform the gas of carbon dioxide, for example, in calcite. So if you have an idea, it would be nice to hear. We can discuss later on. Okay, so nobody is any longer talking about acid rain in Germany and the problems of our forests due to the technical solution by forming gypsum. Another classical environmental impact of large-scale mining with low grade and high tonnages is the so-called tailing plants. That means if I mine out an ore, only maybe less than 1% are all minerals. The rest is gangue minerals like quartz, feldspar, some, let me say, biotite, whatever. And these minerals had to be separated from the ore minerals because I only want to have the ore minerals. I'm not interested in quartz and feldspar. That means there are some processes, it's called flotation, by some chemical reactions. I can separate the ore minerals from the gangue, and the gangue minerals are pumped in huge lakes made out of mud and some chemicals, and to protect these huge lakes, they make a dam. But the dam is also made, the dam is also made out of these sands. But if you have a strong rain, the dam is eroded, and in many cases, the tailings ponds, they are just flowing down into the rivers. And as you can see here, there are some sulfides left, so you have, let me say, a very low pH. It's small acids which are present in these lakes. Well, so here we start with our international cooperation, 100% financed by the Federal Ministry of International Cooperation. And as you can see here, we are looking on georisk, on groundwater, and mining and raw materials, and environmental geology. And as you can see, in many developing countries, from Far East to Africa, even to South America. And I will show you some example of some ongoing projects. For example, in Mozambique, as I told you, we are trying to strengthen the institutional capacities in the mining sector. We are looking for planning and decision making. We are making capacity building. We want to improve the environmental protection, especially when a mine is closed down. In many cases, international mining companies, they go into a developing country, mine out the valuable ore minerals, and then they disappear, leaving back the mine site just as it is. So here we started in order to get a real good structure and to think about mine closure, and taxation is also a problem, especially if you have corrupt administration. And so all the let me see, benefits, the royalties, which is paid by the mining company, disappears anywhere but not there where it should be. So there's a lot to be done. And of course, beside of, let me say, so-called small-scale or artisanal miners, there's a lot of illegal mining ongoing. I will tell you later on about these conflict minerals and the warlords in these areas. So there's a special challenge to solve. Same holds true for Burundi. Here we have an ongoing project with good governance in the mining sector. You can see here there is a lot of Burundi is rich in nickel sulfides, and they have an administration, and they have some maps where they have the claims for the different countries. But there's also small-scale specimen mining where they mine out nice specimens for mining collections or mineral collections. Another example from Africa, it's a supra-regional Africa. You can see here, it's the regional certification mechanism of the Great Lake region here in Central Africa. You know the problem behind. There are a lot of minerals. It's the so-called tin, tungsten, tantalum, and gold, the 3T and gold. These are minerals we are using in the mobile phones, in our electronic devices, and so on. And our question is, as we have heard yesterday from the Rubins from Greenland, they want to detect whether it comes from Greenland or not. We want to be sure when it comes out of the Great Lake region, where the tantal concentrates, or the tin concentrates, or the tungsten concentrates are coming from. So we can make, with our analytical tools, a real kind of fingerprinting, which is similar to the DNA tests you know from each, let me say, film on criminals. So we have here the tools that we can even trace back a mineral concentrate to the specific mine site, some 100 meters, let me say, right or left from the point where the mineral was found. Same holds true for the Democratic Republic of the Congo. Here we support the Congolese mining ministry to certificate. Here you see they are very, very primitive mines where the people are digging out the tungsten and tin minerals, like you can see here, typical concentrates, like we did in medieval times. And then out of these condensers are formed. And the reason why our handies and mobile and iPads are getting smaller and smaller from each year to another is that you can see here, these are these tantalum condensers. They have the same capacity, but they left more or less 70% in size with the same capacity of the condenser. Well, and of course, here an example from Asia. We are carrying out workshops like this one here, where, for example, I took part last November in Laos, where we have 12 member states from Cambodia, China, Indonesia, Japan, Korea, Malaysia, Papua New Guinea, Philippines, Singapore, Thailand, Vietnam, and Timor. That means, again, here we exchange our experience, how to organize mining administration, how to organize the environmental monitoring in the surroundings of mining activity from the beginning of exploration down to the closure of the mine. So the whole cycle is included, and this is done by, for example, this exchange of experiences on these international workshops. Well, coming to the end, coming to the conclusion, that means we all need mineral resources and minerals every day, every minute, all around our life. Most of the mineral sources are not renewable. They are formed by special geologic process in a specific location. You cannot transform them. They are unique. There are no deposits which are more or less the same. So, green or sustainable mining, in sensu stricto, is not possible. If once a mineral is mined, you cannot put it back in the same position. There are some ideas. There are some solutions. That means a responsible use of natural resources. For example, having common goals and creating shared values. So think about the paradoxon of plenty. In many cases of the world, and I have been in 300 mines worldwide, this is the closer surrounding of the mine. They have nothing. The people living, they have oil, they have polluted waters, but they have nothing else. They do not benefit from the mining operation. That's done by international companies. There is, of course, a change ongoing, that only, let me say, 10% are international specialists, and 90% of the employees of the mine come from the surrounding villages. But, of course, mining today, it's a high-specific job for engineers. So what they are doing, they are in the kitchen, or they are making some security services. Anything else is done by the specialists. So, of course, we are discussing, and you have discussed in this workshop as well, urban and waste mining. The idea of recycling, it's great. But we have heard even yesterday the difficulties. There are some elements, some metals we can remelt very easily. Some others, like the rare earths, which are not rare, in fact, are more difficult to separate. So, of course, we are, let me say, as Homo sapiens, being here on this planet for 160,000 years. Homo sapiens. All other hominids died out, like Neanderthaler, Cro-Magnon, and so. They died out. And only Homo sapiens, our species, gets such a big success, coming to 7 billion individuals. But in a complex system, if one individual gets an overwhelming part, the whole system gets a problem. So within 200 years of industrialization, for example, we are mining out, we are producing oil and coals and minerals and fuels of 350 million years of Earth's history. That means in 1 year of industrialization, we consume 1.5 million years of Earth's history. That's sustainable. Okay, thank you very much for your attention.